project. And this is a joint work with my student, Jonah Bertrand, and we hope to have it out on the archive soon. So let me tell you kind of the big picture, and then I'll define everything. But so around 70s and 80s was a lot of work on the tilting theory, or now so classical tilting theory. And since then, there have been numerous generalizations, but in 2010, there was a nice generalization in the world of tau tilting theory. And then sort of tilting theory is always thought of as being contained inside of tau tilting theory. And today, I want to sort of make arguments, maybe not necessarily fully convince you, but make arguments that actually, well, tau tilting theory can also be thought actually a special case of tilting theory. So we can kind of think of it the other way around as well. That's kind of the idea. Okay. Apologies. Okay. So the plan for today is first I'm going to define what I mean by this classical tilting theory or just tilting theory. And then I'm going to define all the notions I need from tau tilting theory, which you may already know many of these, so that's great. And then the main tool we're going to use is this duplicated algebra lambda bar. So we're going to start with an algebra lambda, and then we're going to pass to this bigger algebra lambda bar. And then for sort of the second half of the talk, we're going to investigate the connections between the tau tilting theory of lambda and tau tilting theory of lambda bar. And they are very closely related, as you shall see. Okay. So let me start with some basic definitions and notation. So lambda is going to denote a finite dimensional associative algebra over an algebraically closed field K. Okay, so just think of path algebra over quiver modulo relations. Mod lambdas denote the category finite dimensional lambda modules. And I'm going to also use this notation a lot. So for a module M in mod lambda, I'm going to write absolute value of M, and I'm going to call it the size of M just for short. It's really the number of indecomposable direct summands of M up to isomorphisms. So I take an M, I decompose it into decomposables, and then I count the number of them up to isomorphisms. And so, for example, the size of M is the size of M plus M because the number of indecomposable up to isomorphisms doesn't change. Okay, so it only counts distinct indecomposables in there. And then, well, there was the tilting theory. So there's this very famous theorem, tilting theorem of Brenner and Butler, which appeared in, I think, 1980, there was also early work of Auslander, Platzek, and Ryden, as well as Bernstein, Gelfand, and Ponomarev and reflection functors, which can also be thought of kind of before tilting theory. But kind of the ingredients were already brewing there. There are also a work of Happel and Ringel, believe they defined the tilting module, and then there was a work of Unger on the tilting poset and so on. So many people worked on it. It's a really big and beautiful topic. There's a nice book on it by Assem, Simpson, and Skowronski on tilting theory, which is where you can find a lot of the background that's also here. All right, so I'm not going to need all of the tilting theory. I'm just going to define the things that I want. And really, the main object we're going to look at is the tilting module. Okay. So in module T in lambda is said to be tilting if the following three conditions are satisfied. First, T is said to be rigid. And so what I mean by this is that it should have null self-extensions. The projective dimension of T over lambda has to be at most 1. And so this is quite a strong condition, right? If you start with any arbitrary algebra lambda, projective dimensions of modules can vary, quite large, be infinity, and so on. And so this is a quite strong condition. And then the last condition is sort of the maximality condition. It turns out that a tilting module can have at most the size of lambda, number of indecomposables, and so it cannot have more than that, and it's said to be tilting if it is maximal. So in particular, a tilting object module is maximal module that is both rigid and has projective dimension at most 1. Okay. So some example. Okay, easy example. So suppose lambda is a path algebra over the A2 quiver. Then here's the AR quiver of mod lambda. What are the tilting modules? Well, okay, so I have copied the tilting condition here. So because this is a hereditary algebra, the projective dimension is always at most 1, so that's automatically satisfied for anything. This tells us that the number of indecomposable must be 2. Okay, perfect. And then, so I just have to really check the extension condition. And so, for example, 2 plus 1, 2. So that's really the direct sum of the projectives. That's a tilting modules. They don't have any extensions. And for any algebra, the projectives always form a tilting module. And here also, the other one is the injectives. Turns out to be the injectives, 1, 2 plus 1. Again, that doesn't have extensions. So the only other thing you might have tried is 2 plus 1, but the simple in 2 and the simple in 1, they have an extension, and so that wouldn't work. So in this world, we just have 2 tilting modules. And then by tilt lambda, we're going to note the cell of all tilting lambda modules. And then this is a poset, and the order is defined as follows. So we say that one tilting module T is less than or equal than another T prime if and only if there's this containment of FAC, where FAC of T is contained inside of FAC of T prime. And what do I mean by FAC? So FAC of a module is the set of all lambda modules such that there exists a surjection from some number of copies of M onto X. So you should think of it as FAC of M as all the possible quotients of direct sums of M. And so whenever this FAC condition is satisfied, we say T is less than or equal to T prime. And so again, in our example, we had 2 tilting modules, so I can calculate their FAC. So the first one was the projectives. FAC of the projectives is everything, because everybody is a quotient of projectives, so we have the entire module category. So that will be your top element in the poset, always. And then in this case, the other tilting module was 1, 2 plus 1. So you look at the FAC of that, and well, let's look at the AR quiver. So the quotients of 1, 2 plus 1 is certainly 1, 2 plus 1. And there's no way you can get 2, the simple in 2 as a quotient of these. So the FAC is smaller, and so the tilting poset just has these 2 elements with projectives at the top and the injectives at the bottom. All right. Now we're also going to need something called a partial tilting module. So again, this is the definition of tilting, and I say in my module is partial tilting if it just satisfies the first 2 conditions. So it is rigid and it has the correct projective dimension, but it might not have this maximal number of summons. And then there's a nice theorem that tells you if you start with a partial tilting module T prime, then you can find a T double prime such that the result is a tilting module. So given a T prime, you can add to it some T double prime such that T is, again, a tilting module. Okay, so you can always complete your module, partial tilting module, to a tilting module. And then definition / theorem is that okay, so first I start with some partial tilting module T prime, and then I look at the set of all the tilting modules containing T prime as a direct summand. So in particular, I look at all the possible ways to complete T prime to a tilting module. And then the statement really is that this actually forms an interval inside the tilting poset. That's right. And so the top element is this Bongard's completion, and the bottom element is Bongard's co-completion. All right, so we have these intervals that you can always, the Bongard's intervals, which come from completing partial tilting module. So for example, in our, again, A2 quiver, well, what are the partial modules we can try? We can try the indecomposable. So my T prime is 2. I look at my tilting poset. I look at everything which contains 2. There is only this entry. And so the Bongard's interval is just a single point, so a single object. If my T prime is 1, again, I look at all of these which contain 1. So this is just, again, a single tilting object. So again, it's just a single element here. Well, and my T prime is 1, 2, then, okay, everybody here contains a 1, 2. So here you go, that's my tilting module. Okay, so that's all I want to say for the tilting theory part. Okay, let us move on to now tau tilting theory. Okay, so what do we have here? So I'm going to follow the kind of conventions and setup of Adachi Yaman Raiten, who introduced this in, I think, 2010. Okay, so so here I start with a pair of objects, so M and P lambda. So M is a lambda module, and P lambda is always going to be a projective lambda module. So the first entry is allowed to be any module, the second entry has to be a projective. And this pair is said to be a support tau tilting pair if the following three conditions hold. So the first condition is that there should be no harms from M into tau M. Tau is the Ausland-Raiten translation. The second condition is that harm from this P lambda into M is 0. So in particular, the module P, the module M, is not supported at any of the vertices of the projectives P lambda. Okay, so they somehow like the complement. One is the complement of the other. And then, right, and then we have this, again, maximality condition. This is supposed to parallel the definition we saw for tilting module, is that the number of summons in M plus the number of summons in P lambda has to be the same as the size of lambda. And again, if you're thinking about a quiver, this is the number of vertices in a quiver. And as before, if you just, this is again the maximality condition, if you just satisfy the first two, you're set to be tau rigid. So you can be either a tau rigid pair if I say it's both M and P lambda, or you can just be a tau rigid module if I just specify M. So then that would just mean you have to satisfy the first condition only. And then I'm going to denote by S tau tilt lambda. This is the set of all support tau tilting, I guess, pairs. Should be really pairs or modules. And again, as before, this is a poset where one pair is less than or equal to the other pair if and only if you have this fact condition. So fact of M is contained inside of fact of M prime. So I don't really, so these projectives in the second spot do not contribute, so that you don't really see them here. Only the first one matters. Okay, so two notes I want to make here is that the tilting poset is naturally contained inside the support tau tilting poset. And how so? So starting with the tilting module T, I can create a tau tilting pair where I put T in the first spot and I put 0 in the second spot. And well, let us observe whether the conditions are satisfied. So I do have the right number of summons because my T was tilting, so the third one's satisfied. I have no projectives, so the second condition is again trivially satisfied. And this fact that home from M to tau M is 0, well, if my tilting module, if T is tilting, then it has projective dimension less than or equal to 1 and has X between T and T to be 0. And if you apply the AR formula, Auslander-Raiten formula, it tells you that X between T and T is precisely isomorphic to dual of the Hom from T to tau T, and so that would also be 0. So both conditions are needed here, and so tilting module is automatically then a support tau tilting module or object, and so again this also preserves the order on the poset. So tilting poset is a subposet of the support tau tilting. Okay, this is really kind of a key idea here. Right, and so again, so this kind of emphasizes the fact that support tau tilting theory is a generalization of tilting theory because these tilting modules are always support tau tilting. And then lastly is if I have a pair, support tau tilting pair, M and P lambda, then actually M determines the P lambda, as we kind of observed before, because P lambda is somehow the projectives that all the vertices or that the module M is not supported at. Okay, so sometimes I will omit the P lambda and sometimes I won't. So I try to keep it, always try to do pairs, but sometimes for notation I just write M instead of M comma P lambda. But you're not missing any information here. All right, so an example is, again, we have our A2 quiver, and okay, so now I want to construct my support tau tilting poset. In this case, it's a pentagon. So here we see the tilt lambda embedded inside of support tau tilt lambda. So here the projectives comma 0 and the injectives comma 0. Okay, that's the tilting poset on top. And then there are these other entries in the support tau tilting poset that are not tilting modules. So for example, the simple in 2 comma projective in 1. So certainly 2 has no self-extensions. And the home from P1 into 2 is 0. So this is a support tau tilting pair, and so on. And the bottom element here, as you can see, is 0 comma the direct sum of the projectives, or 0 comma lambda. And so that is always the case. So in general, you should really think about this type of picture. So your top element is always lambda comma 0. Your bottom element is 0 comma lambda. And at the part of the top, we here have the tilting poset here somewhere. Okay, one more slide with some kind of notation definitions that we need. Last one is that similarly to what was happening in the classical tilting story, we also have the notion of completion. So every tau rigid pair, tau rigid means it not necessarily has this maximality size, can be completed to a support tau tilting pair. Great. And then again, we call the interval of all tau support tau tilting pairs that contain this tau rigid pair M comma lambda, M comma P lambda, the Bongard's interval. And again, it's really the same picture we had before. At the top, you have the Bongard's completion, and the bottom, you have Bongard's co-completion. And this, right. And I'm going to denote this interval as support tau tilt lambda subscript this tau rigid pair M comma P lambda. So that's the Bongard's completion of this pair inside of lambda. And then just sort of another thing which is kind of very nice and very important for tau tilting theory, or at least one aspect of it, is that every tau rigid pair that is almost maximal, so the size of it is lambda minus 1, so it's just missing one summand, and then it can be completed in exactly 2 ways to a support tau tilting pair. And in particular, the Bongard's interval is just has two entries, the top element and the bottom, different ways you can complete it, and going from top to bottom is the mutation. And that's really one of the sort of big, one of the motivations for studying and being very much interested in tau tilting theory, and why it is so appealing is because, well, you have this mutation notion in the module category of every finite dimensional algebra. And so this generalizes the notion of like cluster algebra mutations and so on, which is closely related to then the tau tilting theory of Jacobian algebras. So it kind of generalizes, it brings this type of cluster algebra mutations into the module category of every finite dimensional algebra, and also is also very nice in studying cluster algebras via this categorification. So that's like a really interesting appeal of this tau tilting theory. And so, okay, so summary, I guess, what we just talked about is, well, tau tilting theory, again, generalization of tilting theory, because this tilting poset is a subposet of the support tau tilting poset. Perfect. And so the idea I want to kind of try to bring to you today, you can tell me if it's successful, is, well, the idea is I can realize a tau tilting theory of one algebra as actual tilting theory for a slightly bigger algebra, and the two are quite closely related. And so the story is that I can then view again, tau tilting theory as a special case of tilting theory, but for a slightly bigger algebra. And so I want to study, for example, tilting theory. I'm just going to study, sorry, tau tilting theory. I'm just going to study tilting theory for this particular sets of algebras. And then I'm not losing any information. It is all pretty much there, at least from this perspective. Okay. Okay, thoroughly finite tilting theory, maybe, where I have these tilting modules. Okay, so let me try to now tell you what I mean by this in more detail. So I'm going to start with an algebra lambda, and I'm going to construct this duplicated algebra lambda bar. And so it can be given as a matrix algebra in the following way. So I take 2 copies of lambda, and then that's the term for duplicated algebra. I really do take 2 copies of lambda, and I glue them along this bimodule d lambda. And really the picture you should have in mind is as follows. This lambda bar is going to contain these 2 copies of lambda, and I want to distinguish between them. They are really the same, but I'm going to denote one as lambda and the other one as lambda dot, because I want to distinguish between them. And then, so you have this lambda here, you have this lambda dot here, and okay, so think of this as a quiver. I have the quiver for lambda down below, I have the quiver for lambda dot above, and they are the same quiver. I'm just going to dot all the vertices that I had here in this copy. And the only arrows, the new arrows we're going to have from this bimodule structure is I'm going to have arrows from this copy lambda dot into this copy of lambda. Okay, and here are sort of really the key properties of this duplicated algebra. Is that, well, already looking at this picture, the projective of this lambda bar at the vertices I, which are vertices here, these are the same as projectives at lambda at I. So projective lambda modules are also projective lambda bar modules. Similarly, the injectives then at the dotted vertices, these would be the same as the injective at the dotted algebra of the dotted vertex. And then, for what about all these new ones that you're going to get? So the projective at the dotted vertex here, so this will be different because you're going to have all the projective at the dotted, plus you're going to be able maybe to go down and get some vertices of the lambda as well. And so sort of from this definition, it follows the projective at the dotted vertex is the same as the injective at the non-dotted vertex here. Okay, so you can go all the way here from the vertex I dot all the way to the vertex I here. And then there's the short exact sequence. So this projective injective in the middle. We said that we have this projective at the dotted part here. And what happens is you have the injective at the non-dotted part on the other side. Okay, so I'm going to show you an example now, or 2 examples. Okay, so lambda is going to be my path algebra of a 1 vertex quiver, no arrows. Okay, and so what is my lambda bar? I take a copy of my initial quiver and I put dots here at the top. I put just the lambda quiver at the bottom, and I connect them with some arrows. And well, in this example, you're just going to have 1 arrow from top to the bottom. And then you can check that, for example, the projective at the dotted part, the 1 dot 1, that's the projective. It's a submodule of it is the 1, which is the injective at the 1. And the quotient is 1 dot, which is the projective at the 1 dot if you ignore the bottom stuff. Okay. So here we have, so here's another example, slightly bigger. So here's the A2 example. And then if you look at the lambda bar, then again, here I copy the A2 quiver with dots. At the bottom, I just have the lambda, and I need to add some arrows from top to the bottom. And it turns out in this case, you add arrow beta from 2 dot to 1. And the relation is that the composition of these 3 is 0. So alpha dot beta alpha is 0. And again, you can check that the conditions are satisfied. Why are you frozen? Okay, so here's what I want to say about duplicated algebras. So what's going to happen next? I'm going to relate mod lambda to the category of this mod lambda bar, this duplicated algebra, via two maps, and I call these F and G, such that they behave well with respect to tilting or support tau tilting theory. So I'm going to go from mod lambda to mod lambda bar, and such that I'm going to have some sort of embeddings from support tau tilting of lambda into support tau tilting of lambda bar. And so automatically you see already two maps. There's mod lambda is included inside of mod lambda bar just via identity, but that's not the right map. That's not going to behave well with respect to tilting and tau tilting theory. Okay, so really that one is not a good one to think about it. Okay, so let us start with the map F. So what is that? So I start with a module in lambda, and then you consider its min projective presentation in mod lambda. So M, some P0 lambda, P1 lambda. And then I'm going to construct this F of M as follows. So the way I'm going to present it maybe is not clear that this is well defined and so on. But this is the way kind of you want to think about it. So I start here at the bottom with the same projective presentation of M in mod lambda. And then I'm going to construct F of M by constructing its projective presentation in lambda bar. So what I do is, in position 1, I'm just going to copy P lambda 1. And so remember from the slide before, projective lambda modules are also projective lambda bar modules. So this is a projective in mod lambda bar. That's great. And then I had this P lambda 0 here, and I'm going to copy it here as well. And then what I want to do is, so the key is I want to add here some P lambda bar. So what is this? This is now a projective injective lambda bar module. So it's the projective at the dotted vertices, and I want to add it such that the map here from P lambda 1 into P0 plus whatever I added becomes injective. Okay? I really want this map which was here before, which was not necessarily injective. I want to make it such that this is now injective. And so you can always do this, and I want to do it sort of minimally. I don't want to add too many repeated summands, and if I do this, I can then, my F of M is then defined as the co-kernel of this injective map. Okay, and then, well, you see that there's this nice surjection from F of M to M. Okay, so automatically, what do you see from this diagram is that, well, what F of M you created is that it has, you see its projective presentation here, and it has projective dimension at most 1, okay? So the projective, sort of by construction, the projective dimension is at most 1, which is nice. Moreover, we can show that this is an if and only if statement. Okay, sorry. Moreover, we can show that if whenever you start with the M and its projective presentation already stops here, I can put 0 here and this map is already injective, well then F of M is already isomorphic to M. Okay, so that's nice. So if M has projective dimension at most 1 already in lambda, you're not doing anything, and this F functor is identity. Map, okay, it's not a functor, it's a map. And moreover, we can say precisely what the image of this is. So this F map is actually an inclusion, and we can say what the image is. So the image is the set of all lambda bar modules whose projective dimension is at most 1. Perfect, we've just seen that. And moreover, X, we have to exclude certain summands from X. X is not allowed to have summands which are projective injective lambda bar modules. Okay, and there's this other set of objects here, and it's not allowed to contain summands from the omega inverse of lambda bar. So this is co-syzygy of projective lambda modules inside of lambda bar. Okay, you take a projective lambda module, you embed it into the injective, and you take the co-kernel. Okay, so you have to exclude those summands as well. So sort of again, they have projective dimension 1 in lambda bar, but they are not in the image of F. And I'm going to denote this image of F as H, sort of the hereditary part. That was my idea, sort of behind the H, the hereditary part of lambda bar. so this is really the key property, the projective dimension less than or equal to 1, apart from these finite number of summands. Okay, so let's look at an example. So here's our A2 example, AR quiver. And so the lambda bar we saw from before has this 2 copies of lambda modulo the composition of 3 arrows is 0. And so here's the AR quiver of lambda bar. And let's look at my functor f. So I said, if the projective dimension is already 1, the f functor is identity. So I'm just doing identity. So this 2, 1, 2, 1 is embedded into 2, 1, 2, 1. That's the image of f. And now what else is here? Let's just look what else is in this module category. Well, there are these projective injectives at the dotted vertices, okay, which are not in the image, but they have projective dimension -1. And then, as I said, we have this strange things that are cosyzygies of projectives. So again, let's just check that these are the ones. So what do? I look at the projective modules here, but inside of the lambda bar, so 2 and 1, 2, and I embed them into an injective. So 2 I can embed into this this is the projective injective into here, and the co-kernel is 2.1, so that's this. And similarly, 1, 2 I can embed here, and the co-kernel is 2 dot. Okay, so that's the 2 gray ones. That's this omega inverse. And then this is really where the project started, because I learned about this result, older result, at a conference once, is that this is kind of an older work of Asim, Brusler, Schiffler, and Todorov. This predates support-out tilting theory. And it says the following. So if lambda is a hereditary algebra, then the tilting lambda bar modules, so tilting modules over the duplicated algebra of a hereditary algebra, are in correspondence with cluster tilting objects in the cluster category C lambda. Okay, so if you don't know what that means, that's okay. As I said, support-out tilting theory wasn't there. So here, after the support-out tilting theory was involved, this is the same as support-out tilting theory of lambda. Okay, so in the case of hereditary algebras, it is known that the tilting modules over the duplicated algebras correspond to support-out tilting modules of lambda. And so in this case, the functor f, because this is a hereditary, the functor f really does this, but the functor f is really an identity here. So it's really not doing much. And so now kind of the point is we have now this f for more general ones, and we generalize this statement for arbitrary algebras. Okay, so let me show you another example where maybe f is not identity, so to see kind of how you work with it. So a non-hereditary. So suppose K is this path algebra 1, 2, 3, where I have the relation from 1 to 3, so hence the dotted here. So the projectives are 1, 2, 2, 3, and 3. Now the duplicated algebra, again, I take 2 copies. This is the dotted version with the relation. This is the non-dotted with the relation, and I have some arrows going down. And the relations are such that, okay, so you have the dotted relation at the top, you have this relation at the bottom, and the only other relation is this commutativity here. You have this commuting square. So these become the new projectives at lambda bar. And so here's the AR quiver of lambda, and this is the big AR quiver of lambda bar, and you have what I claim is to be the map F. Okay, so this kind of embeds here into this blue part. As before, the orange are the projective injectives, the gray are now the omega inverses of projectives. And so let's just calculate F. So there's, since, again, F is only interested if you're non-hereditary. So the only module here which has projective dimension not 1 is the simple in 1. So let's try it there. So if I look at the simple in 1, its projective cover is P1 here, and the kernel is 2, so the projective cover of the kernel is 2, 3. So I have P2 going into P1. And now I'm going to try to construct this f of m. So I start with this P2 and the map going into P1. So that's, where's my P2? So 2, 3 going into 1, 2. But this is certainly not an inclusion. And so I want to supplement with something with the projective injectives, I said I do get an inclusion. So in this case, I can add the projective at the 3 dots. So these are my projective injectives at the 3 dots, 3 dot 2, 3. So I embed it into both here and here. And then you can take the co-kernel, and that's the 3 dot 1, 2. So this is my f of m. Okay. And this is really the only choice that you can do. Okay, so something does change. This is really, so I'm setting 1 to this 3 dot 1, 2. So it's really does become different. So what are now the key properties of this map? So the first sort of really result is that if I start with tau rigid lambda modules, so this f, I want to say that this f behaves well with respect to tau rigidity on one side and tilting properties on the other side. So if I start with a tau rigid lambda module, so I mean module m such that there's no home from m to tau m, and I apply this functor f to it, then what I get the partial tilting lambda bar modules in this my subset H, hereditary part. And so I mean here that x1 between f of m and f of m is 0. Okay, and so this gives you a bijection. Okay, very good, a correspondence. And now I want to enhance it sort of such that I get a bijection that I want between tau tilting pairs and actual tilting modules. So what I do is I create this m bar. So this f bar is going to go from tau tilting set to tilting set of lambda bar, and it's going to send a pair m comma p to the following tilting module. It's going to take f of m, perfect. Then what do I do with this projective? Well, I apply exactly this functor, omega inverse lambda bar of the projective. So this is this gray module that we've been denoted. This lies in this gray part. This lies in this blue part. And to be a tilting module over lambda bar or over any algebra, the projective injectives are always a summand. Okay, so you have to add in the projective injectives. So the fact that the number of summands here is the size of lambda tells you that this is also the size of lambda, so f preserves the number of summands. And then you have to add lambda more summands to make it a tilting object, because you need 2 times the size of lambda, because that's how many vertices are here. And so the projective injectives do the job. And so in particular, what we show is that this map f bar is actually an order preserving bijection from the support tau tilting poset to the tilting poset of lambda bar. And so that's kind of, this is quite interesting. It tells me that the tilting posets of duplicated algebras precisely capture all the information of a support tau tilting theory of an algebra lambda. Okay, so in some sense, like tilting theory is more general than support tau tilting theory, because I can make a particular restriction and then I can study it's if I just like focus on duplicated algebra, then I recover all the support tau tilting theory that I want. So that's kind of, I think, quite interesting. So let's look at this map f bar. In the A2 case, what do we have? So this was our support tau tilting lambda. So my f bar, because again, this is hereditary, the f map is actually identity. So here I have 1, 2 plus 2. So I'm going to have 1, 2 plus 2. And then this is 0, so I don't have any of these omega inverses. And then I also add in projective injectives. So, okay, so here I forgot about the projective injectives. I didn't write them everywhere, but they should really add them to every summand. For example, this one, this is going to be 2, 2. And then, what is this? P1. Right, so I have to do the omega inverse of lambda bar of P1. And if you go back, this is actually would be the 2 dot. And so on. Okay, so for example here, 0 times and these two direct sum of these two projectives, this would be the omega inverse lambda bar of the projectives, and that's the 2 dot 1 and 2 dot, and so on. Okay, and this is the tau tilting. This is the tilting poset of lambda bar, and I'll show you a kind of bigger picture later on. But yeah, but that's the idea. Okay, so that's like the first map F, and now I want to tell you about the second map G that we have. And then together F and G kind of give us some more information about the support tau tilting poset of lambda bar. Okay, so the second map is G, and I similarly defined it on projective presentations. But first I'm going to define it on projective. So if I have a projective P lambda Okay, direct sum of indecomposables with some multiplicity. Then I define G of P lambda projectives, but now at the dotted part of my duplicated algebra. So these are now projective injectives, okay? These are the projective injectives at the duplicated algebra. And then, well, I start with a projective presentation of M in lambda, and then I apply G to the projectives here, and then I also get associated map from F to this G of F, and I take the co-kernel as before, and then I declare this to be G of M. So G of M is the co-kernel of this G of F map between the projectives. So these are again now projective injectives. Okay, so now let's look at this. So this G is now definitely not an identity map. Right, so what happens to the projectives under this map? So the projective presentation of projective is just P0. If I replace P0 by the dotted part, I get the projective at the dotted vertex. So the 2, for example, the projective at 2 is sent to the projective at the dotted vertex. The projective at 1 is sent to the projective at the dotted vertex. So the only non-trivial or not so trivial thing is what happens to example the simple in 1. So simple in 1 has the projective presentation P1, P2. So here I'm going to look at the P2 dot mapping into P1 dot via the same map. And so the co-kernel into this case is 1 dot. So I'm sending 1 to 1 dot. So in generally, the dotted part, like 1 is a quotient of the other. So normally G of 1 would map into like M dot, whatever object here dotted is. In this case, they're just equal, but it's not so trivial in general. Okay, so the images, you have these blue things here. And again, we have this map G kind of also behaves well on the level of support tau tilting modules. So what happens is these tau rigid lambda modules via G are mapped to tau rigid lambda bar modules. And moreover, which ones? These are all the ones which are sort of behave well with lambda. So in particular, there's no home from lambda into tau of these modules. So this means like here I can add in lambda as a direct summand and I would still be tau rigid. That's the whole point. So they are sort of compatible with lambda. And then again, I can enhance G with a G bar. And what I get is I get an inclusion from support tau tilting lambda modules to support tau tilting lambda bar modules, where given a tau tilting pair here, I first apply GM to the M part, I apply G to the projective part, and then as I said, they work well with lambda modules, so I just add in here the projectives in lambda. And this again gives me a bijection, and this is a bijection now between support tau tilting lambda modules and support tau tilting lambda bar modules, which are really all contain lambda. So this is a Bongard interval of lambda inside of lambda bar. And so, okay, so we already have now 2 different ways to embed support tau tilting modules lambda, one into the tau tilting theory of lambda bar, and another via this Bongard's completion of lambda. And you can, okay, so this is an example, maybe for the sake of time, because I want to show you a bigger example instead. So let's go to the theorem, is that the theorem is as follows. So you can now play around with these 2 maps, F and G, and actually get much more. So using this tau tilting reduction of Yasso, we can show that what do I want to do? Okay, right. So if I start with tau tilting lambda, support tau tilting poset lambda, and given a pair M comma P lambda, if I apply G to this, so I get some partial pair inside of lambda bar, but if I look at its Bongard's interval, I recover so the Bongard's interval of this GMP lambda is isomorphic to the support tau tilting poset of lambda. Okay, so this means I get lots and lots of support, lots and Bongard interval inside of lambda bar coming from lambda via this map VM. And in particular, what you get an inclusion of posets, and this really an inclusion, not a bijection, as we shall see, is that I get for every pair, so I get a map from support tau tilt lambda cross support tau tilt lambda, so 2 copies of lambda into lambda bar, support tau tilting theory of lambda bar, by mapping a pair here and a pair here to an object here. And it's not really a precise, super precise map, because it kind of involves this Yasso reduction map, which is also in this direction that I want, is kind of harder to state. But what this does is, given a m comma p lambda cross anything in here, what you so do is you just send it to the Bongard's interval of this gm p lambda. That's the idea. So whatever is here is mapped to the appropriate element in the interval of Bongard's interval of this object. And then as a corollary, we get that. So you've already seen that support tau tilting poset of lambda is isomorphic to tilting theory of lambda bar. And then both are actually isomorphic to this Bongard's interval of lambda bar of the projective injectives. I actually tried proving this directly, that these two are isomorphic. I was having a hard time. So actually, this is a corollary of that, which is much nicer. Okay, so here's, I think, a good example which illustrates kind of what's going on, because at the end, I think it's getting complicated. Okay, so let's do a small example first. So my lambda is just, path algebra of a single vertex. So this is my support tau tilting poset for lambda. And how do I embed it in the support tau tilting poset of lambda bar? So this is the pentagon, the A2. And so first you have this map F bar. So the image of F bar, we said, is the tilting of lambda bar. And so in here, this is everything which has zero that has no projectors in the second component. So that's this. So the map F maps these to this blue color here at the top, tilting theory. Okay, what is the map G bar? G bar is, remember, G bar is the support tau tilting of lambda. Lambda is just this projective at lambda is just the simple in 1. So I look at everything here which contains a 1 in the first position. So that's this one, and that's my image of G bar. Okay, that's the teal, or sorry, the orange. And then what is this map phi? This map phi, which sends pairs of support tau tilting posets inside of here. And so what that is, I look at the top of this orange. So I look at the orange. So this is my orange element, and this is my orange element. And I'm going to look at the Bongard's interval of this. Hold on, which one do I want? In this case, I want the 1.1. So this is the, right. Oh, yeah. So I look at here, I remove the projectives, so projective lambda modules, and I look at the Bongard interval of the other object. So in this case, it's 1.1. So this is the other element in here which contains 1.1. So this is one of these purple things. And here, again, I look at this top, I make this my top element of the Bongard interval, and I remove the 1 in the first position. So what I'm left with is the P1 dotted in the second position, and this would be the Bongard interval of that. So you see these two orange things. This means this is the S tau tilt lambda cross S tau tilt lambda embedded inside the S tau tilt lambda bar, and I don't get everything. For example, this one is not in my image. Okay, so here is a much bigger example. Again, I don't want you to read the labels. Again, I just want to show you the picture. And the idea is this. So you have this lambda bar. Oh yes, my lambda is just the 1 to 2, my lambda bar. So I didn't put the dotted vertices. This uses other conventions, but again, it doesn't matter. It's the same algebra. And this is the support tau tilting poset for that. And the idea is, so what is the support tau tilting poset for 1 to 2? It's this pentagon. And in this picture, I should see pentagon cross pentagon in here. So I see 5 pentagons. This is my top pentagon. These are my other pentagons. That's my pentagon cross pentagon. And these 5 pentagons form themselves a pentagon. That's the point. Going around here is the same as going around here. So that's hopefully the pentagon that you see. And this is the image of this phi map. And this top entry inside of every pentagon, this is the image of G bar map. And so then I take its Bongard's interval and I get these guys here. So here's the connection to maximal green sequences as you know this, let me just briefly say maximal green sequence is a finite maximal chain in the poset support-tau tilting in the support-tau tilting theory that starts from the top element and goes to the bottom element. And MGS lambda, I'm just going to note the set of all maximal green sequences. And then what we get is this inclusion phi actually tells that we also have an inclusion from any pair of maximal green sequences for lambda actually induce a maximal green sequence for lambda bar. Let me not go through this notation. Again, just show you an example what that means. Okay, so this is the support-tau tilting poset for the A2 quiver. And so I choose two maximal green sequences here. Let's say here I choose the short way around, and here I choose the long way around. And so what that means is I'm going to, for example, start with this one first. And in my pentagon of pentagons, I'm going to go the long way around. So here I see the 5 pentagons, and I'm going to go the long way around from the top element. So going from the top element here to the top element here to the top element here to the top element here. That's this, okay? And then after doing this, what you get is you get to this bottom highlighted region, and in this bottom highlighted region is again isomorphic to a pentagon. So in that case, I will now do a maximal green sequences, which now goes short way around, for example. So here I just do the short way around. Okay, so the first one is like really big steps, kind of, you can imagine going around these top elements of these intervals, and then at the bottom you choose, for example, this sequence. So in some sense, what this tells us is that the image of this lambda cross lambda inside of lambda bar spans the entire length of this support-tau tilting poset. I'm not just always somewhere at the top or in the middle or at the bottom. I go like from the top to the bottom. So that's the idea. And you are missing a lot of things. Let me just point out. These are not in the image, and we don't really know. We looked at it briefly, but not much in detail. But there are many things in between, which we're not getting in this way. Okay, so I stop here, and thank you very much.
So thank you very much for your very nice talk. Thank you. Are there any questions or comments? So let me start with some small question. And first, there is one question on the chat from Ramin. Can you see it?
Yes. Okay, I'm just reading it. Do you think that there is a similar bijection between silting modules, infinitely generated, and okay, so I'm definitely not an expert in the infinitely generated things, but certainly something to look at. Yeah, we definitely have not broached that subject at all. Yeah, maybe, yeah, but I don't really have a lot of intuition about the infinite story.
And another question about this question I also had in a finite dimensional case, do you have some results about the drive category? I mean, is the silting complex in drive category? Because as you know, there is a functor from duplicated algebra to the repetitive algebra. And also, if the global dimension is finite, the stable category of the repetitive algebra is equivalent to the drive category. And so maybe there's some connection between the siltings complex in the bounded drive category, at least in case the global dimension is finite, and some objects in this duplicated algebra.
Right. Yes. We have not looked at it, but that's something I think very interesting to think about. I agree. Yes. Yeah, I forgot to mention this. This duplicate algebra is like a truncation of the repetitive algebra. Yes. That's right.
And
Yeah, I don't know. Maybe there's something in that direction. Definitely.
there is
Oh,
also
yes.
some other question on
Right.
the chat.
Is there a relationship between GFAN? Oh, again, not something we looked at. These are all excellent. I haven't, this is like the first time I'm talking about this, so I'm very thankful for all your questions. And but yeah, at this point, this is all we thought about and done. And so definitely not, we haven't not talked about G vectors and G vector fans and what that means. But because these maps F and G, they're kind of defined on these projective presentations, there should, I expect, there may be some nice, you can say something about the G vector fence because you can map these projective presentations to projective presentations. So you may be able to say
Mm.
something. So yeah, definitely something. The
Uh,
thing I was kind of, as I was writing this, I wanted to think about is what happens to the endomorphous algebra. So like the tilted algebra, so I mean, now this lambda bar, I have these tilting modules, and I want to study, maybe that's what I would like to think about as the endomorphous algebra of these tilting objects in lambda bar, and how are they related to, I don't know.
yeah,
Yeah, I
but
guess, yeah. Yeah, so we haven't done anything about the
But
tilting algebras at
I
all.
think there's at least there's some nice question, nice connection between the G vectors because in functor you use just projective presentation and also you fix the power of the projectives. And so I think at least there is some nice connection between the G vectors. But about
That's
the G
right.
vector fun, maybe.
Oh yeah, yes, thank you.
And also there is another question in chat.
Oh, if lambda is tau tilting finite, how about bar lambda?
Yes, this is a very nice question. Because
Also not something we, yeah, I don't know. So again, this maximal green sequencing is kind of nice. Maybe it
yes,
is true
yes.
then that it would be finite, but who knows? Maybe there is a big infinite part in lambda bar on the other side that it's not seen by these intervals, and so yeah, I don't know.
Because as you know, there is at least a lot of conjecture around the total definiteness, and up to now, I think most of them is open, and maybe there is some way to thinking about this conjecture. Uh,
Mm, possibly. Okay, another question. Um, can tau tilting theory of a Jacobian algebras categorify all cluster algebras? Oh, even without Jacobi finite potentials. Yeah. Tau tilting theory is only for finite dimensional algebras. That's true. Yes, and in that case, you have the categorification. If it's infinite, yeah, I don't think anything's known if it's infinite. I'm not sure what fails or exactly what holds and what fails. But yeah. Mm. Yeah, definitely tau tilting theory only works for finite dimensional algebras. Can it be extended for infinite? I'm not sure. And that's
because
what that means with Jacobi, what that means with connection to cluster algebras.
there is a paper by I think Igusa and
Mm.
other people, but they assume that the Jacobian algebra is finite dimensional. They work on Jacobian algebra, but they assume that is Jacobian algebra be finite dimensional. They work on maximal green sequence and the maximal length of the uh, chain in the posets.
Uh-huh, uh-huh.
But in that paper, this assumption that the Jacobian algebra is finite dimensional is essential.
Yes. Yeah, I mean, The Adachi-Yaman-Reitenau tilting theory is only for also finite dimensional algebra. So,
Yes, yeah.
so I don't know what happens if you go to infinite. As I said, I'm not really an expert in the infinite
Mm.
world at all. Yeah.
So, are there any more questions or comments? So if not, let's thank the speaker again. Thank you very much for your very
Oh,
nice
thank
talk.
you. Thank you very much for all the questions. This is
I think this is a very nice results, and because there are connect to this different area, there are a lot of questions and in this area.
yeah, so hopefully other people will try and do something and see like how far can you push
Mhm.
this connection. Yeah. Yeah, I'm really intrigued that this image is